Okay, so we're starting Unit 8. This is the introduction to stoichiometry. So I'm going to deal with three types of problems here. What I call moles in, moles out, which is like mole ratio problems. Grams in, grams out. So, I tell you how many grams go into reaction, you tell me how many grams comes out, and percent yield. So Unit 8 also covers limiting and excess reactants, but I'm not going to do that in this video. So just to kind of define stoichiometry, it's basically calculating the amounts of reactants and products in chemical reactions. So everything we did in Unit 7 was qualitative. You just described what was happening with formulas. Well, now we're going to put some math behind it. So let's start with this example here. So this is an example of a moles in, moles out problem. This is kind of just a phrase that I use. It's not like an official chemistry phrase. Basically, we're going to be calculating... in this case, I say 12 moles of aluminum. So that's the moles going into the problem, and I'm saying how many moles come out. That's what I mean by moles in, moles out. So we have a piece of aluminum burns in air using a Bunsen burner. If 12 moles of aluminum are burned, how many moles of oxygen gas are consumed? And also how many moles of the product form. So we're building on what we've learned. You can't just forget everything you've learned. We're building on naming, we're building on formulas. So the first thing we're going to do is write our balanced equation. So we have aluminum burns in air. That's going to be Al plus O2. Okay, so you have to know that this is going to be a synthesis reaction. Aluminum is going to bond with oxygen, forming Al2O3. And now we go back and balance it. So let's see, 3 O's and 2 O's. So let me put a 2 there and a 3 here, and 4 aluminums there. So what you want to do in these problems is write out the mole ratio. And I kind of prefer to do that right below. On the worksheets that I've given you, I think it says equation, mole ratio, and theoretical. So under mole ratio, I rewrite my coefficients down below. And this just kind of drives the point home that it's a 4 to 3 to 2 mole ratio. And really what that means is if I have 4 moles of aluminum and I react 3 moles of oxygen gas, I'm going to get exactly 2 moles of aluminum oxide here. Okay, so in this particular problem, now we're going to fill in what we're given and what we're looking for. So it says if 12 moles of aluminum are burned. So here's my aluminum. I'm going to put the 12 under here. How many moles of oxygen gas are consumed? That's like the first question I'm asking. So let me put an X there. Let's deal with this question first before the second part. So this is this type of problem. Basically, there's two ways of going about it. You can just sort of look at it and kind of reason through what it's going to be. And by that I mean it's a 4 to 3 ratio. So what would I have to do to go from 4 to 3 in terms of these numbers here? And what I'm thinking is, 4 to 3, you drop that down by 1/4. So I'm thinking of kind of doing the same thing here with the 12. Let me calibrate my board real quick. Yeah, so there's kind of two ways of going about it. And this probably isn't the best example. These numbers are a little trickier, but I'm kind of thinking, 4 to 3, I'm thinking the 12 is going to go to a 9 if you drop it by 1/4. But let's show working it out kind of mathematically. So if I'm trying to solve for this x here, what I can do is say 4 over 12 equals 3 over x. And this kind of makes sense. It's like a ratio. This over that is going to be that over that. So now we can cross multiply and get our answer. So 12 times 3 is 36, and that's going to equal 4x. And now you can see it is going to give us 9. But you want to be careful. Sig figs. If I told you 12 moles, you're going to need to answer with 2 sig figs. So it's going to be 9.0. And that's 9.0 moles of O2. Okay, and that's what my answer would be here. So again, there's two ways of going about it. You can either work it out like this with your cross multiplying, or you could just kind of think about what the ratio is. And again, this isn't the best way to think of it here, but I'll go through the next step. Next one should be a little easier to see. So here it says how many moles of the product form. Well, there's only one product, so we're looking for how many moles of this form. So here's X. Well, again, if we're putting 12 moles in, we want to see how many moles we get out. So you could set it up just like before. Let me kind of erase this extra stuff here. Okay. So we have 4 to 12 here is going to be 2 to x. So we can do the same thing where 4 over 12 equals 2 over x. For this particular problem, we're ignoring this middle part. We already dealt with it. So I'm going to do the same thing with these sets of numbers and cross multiply. So 4x equals 2 times 12 is 24, and that's going to give me, x equals 6. So the answer is 6 moles. But again, 2 sig figs, so 6.0 moles of Al2O3. So you figure that out by cross multiplying. But I think an even easier way to do this one is if the numbers look kind of simple enough, you could just kind of reason this in your head. Here's what I mean. Let's ignore that so we don't get confused. All right, I'm trying to figure out x here. Look at my mole ratio, 4 to 2. It's a 4 to 2 mole ratio, meaning you're going to get half as many moles out as you put in. So the 4 to 2 ratio, think of it as like 2 to 1. Well, when you do the same thing for this number, 4 to 2, the 12 is going to go down by half and go down to 6, and you get the same number. So what I'm trying to get at is be able to do these mathematically with cross multiplying, but if you see a pattern, if you see the logical kind of step, just work through it quicker, because the faster you can do the simple stuff here, the better you can do the longer problems. So let's do another example here, and I hope the font's not too small to read there. But here we have a number that's a lot more complicated than just 12 from before. So we have 0.829 moles of methane combust. So CH4, and since it's combustion, you have to know that it's reacting with O2 to form CO2 plus H2O. So remember, we're not done with formulas. You can't forget all that. So to balance, I say do H's first. H4, so let me put a 2 here. Looks like my carbons are balanced, so now let me just check my oxygens. 2 of those and 2 of these. So this will be nice and straightforward there. So my mole ratio is 1 to 2 to 1 to 2. Okay? So, looks like it's a two-part question. If I tell you 0.829 moles of methane combust, let's write my 0.829 moles down below that. How many moles of carbon dioxide are released? So let's solve this first. Now this is definitely one of those problems you should be able to do real quick right away without cross-multiplying or anything. Notice the mole ratio here. Ignore this 2 for now. We're not dealing with how much O2. We're just saying if you put this many moles in as methane, how many moles are you going to get back out? And notice it's a 1-to-1 mole ratio, so X is going to equal the exact same thing, 0.829 moles of CO2. Now it says how many moles of oxygen gas are consumed. So that's going to be this, how many moles of oxygen gas. So again, you can set it up by cross-multiplying. We can say 1 over 0.829 equals 2 over x. So 1x equals 2 times 0.829, which is going to be 1.66. Let me double check. 0.829 times 2. 1.658, so 1.66. And checking my sig figs, 3 sig figs, 3 sig figs, that's correct. And this is moles of O2. Okay, so that's one way you can solve this, but again, I think even easier, this is definitely a pattern you should be able to recognize. Write this in. If I just showed you this and say solve for x, you should be able to say, well look, it's a 1 to 2 mole ratio. 1 to 2, meaning you're going to use twice as much of this as you do of that. So if you put this number in and it's a 1 to 2 ratio, all you have to do is double it and you'll get your answer. So right away you can just say this times 2 and it'll get you the same number. So that's what I want you to kind of look out for. Okay, and again, this is another moles in, moles out problem. Now the next level up is what I call grams in, grams out. It's the same exact thing, but on the front end, you have to convert to from grams to moles, and on the back end, you have to convert back to grams. Basically, by grams in, I mean, instead of me telling you this many moles of methane combust, I'll tell you a certain number of grams of methane. And instead of saying how many moles of carbon dioxide are released, I'll say how many grams of carbon dioxide are released. So again, all you have to do is convert your grams to moles initially, work through the table, and then convert your moles back into grams. Because everything in this table, all of these units, have to be in moles. You cannot be crossing grams into other grams. So let's go through a couple problems. All right, so 25.2 grams of copper metal. So that's going to be Cu. We can call that solid. Assume 3 plus charge, completely burn in air, so plus O2 gas. And if we're assuming it's forming a 3 plus charge, it's going to be copper with a 3 plus bonding with oxygen. So Cu 3 plus, O2 minus, crisscross, you get Cu 2O3, synthesis reaction. Now we need to go back and balance this, so I'm seeing O3, O2. Let me put a 2 in front of that and a 3 in front of that, and it looks like that gives me 4 of these coppers. Okay, so my mole ratio is 4 to 3 to 2. It says if 25.2 grams of copper go in, what mass of copper 3 oxide, which is this, forms? So what I cannot do is this, 25.2, 4 to 2 ratio, what's that going to be? You cannot do that because grams of copper are very different from grams of copper 2 oxide, copper 3 oxide. You cannot do that. So what we do is we first convert this into moles. So this is like a separate little calculation. I'll do this one right down here. So I'm going to have 25.2 grams of copper. And now you're going to use your periodic table, which I don't have in my hand, but I got one right up there. And the number you're looking for is underneath. That's the molar mass. And remember, that's the number of grams that equals 1 mole. So under copper, it says 63.546, 63.55 we'll say. And that's the number of grams that equals 1 mole. So when I'm converting here, I'm going to say 1 mole over 63.55. 63.55. Okay, grams cancel grams, and this will get us into moles. 25.2 divided by 63.55, and this gives me 0.3965. I'm kind of going extra sig figs here. I can tell that's going to end up being 0. The 5 rounds of 6 up, the 6 rounds of 9 up. It's going to be 0.40. I'm messing up here. 5 rounds of 6 up, but we'll stop there. 0.397. And that's moles of copper. So this number is going to go in my table. 0.397. Okay? So now that I have moles of this, I need to find moles of X. Because it says what mass of copper 3 oxide forms. So again, at this point, you have 2 options. You can work it out using the cross multiplying, where I would say 4 over 0.397 equals 2 over x. 4x equals 2 times that, and you get your answer. But what I would prefer to do in this case, this looks like a nice, easy mole ratio for me to see. So it's a 4 to 2 mole ratio. So in other words, for every amount of copper you put in, you get half as many moles out as copper 3 oxide. So what I'm going to do is take this number and divide it by 2, cut it in half, because it's a 4 to 2 or a half ratio. So I'm going to say 0.397 divided by 2, and with my 3 sig figs from the problem, the answer I get for x is it says 1985. That's going to be 0.199 moles, not grams, moles. And that's moles of Cu2O3. Okay? But we're not looking for moles, we're looking for mass. So we got to do one last step. I got to convert this into grams. So let me look at my periodic table. I'm going to go 2 coppers, so that's 63.55 times 2, plus 3 oxygens. Remember, we treat oxygen like 16, so 16 times 3 is 48. I'm just going to add 48 to that. And let me set this up here. So it's 0.199 moles. Now my calculator tells me the molar mass is 175.1, and that's grams per mole. So I'm going to say 175 0.10 grams per mole. Mole cancels mole. And let's see what we get. So with 3 sig figs, I get 34.8. Let me write it over here. A little messy here, but 34.8, and that's grams of Cu2O3. So that's my final answer. So again, it's the exact same thing as a moles in, moles out problem, but you just do one step on the front. You had to convert the grams into moles. Then you plug it into your table, and then you get your answer in moles, but then you do one more step, convert moles into grams. Let's do one more. All right, this says 4.37 grams of potassium phosphate are added to excess lead-2 sulfide. What mass of precipitate should form? So let's write out our equation here. So K3PO4, that's potassium phosphate, added to lead-2 sulfide plus PBS. Now in this particular problem, remember, in order for this reaction to take place, they can't both be solids. They're really going to be aqueous. But technically, if I said 4.37 grams of aqueous potassium phosphate, that's, there's a lot of that water that's unaccounted for. So really, what this really means is you take 4.37 grams of the solid, dissolve it in water, but that's still like the active ingredient. That's what's going to be happening here. So I could still convert that to moles and use it. But let's finish out our equation first, and let me recalibrate this board. It's giving me trouble here. All right, so the potassium is going to bond with the sulfur. You have to know how that happens. K2S. The lead-2 is going to bond with the phosphate, forming, let's see, the lead is 2, the phosphate is 3, so it's going to be PB3, parentheses, PO4, 2. Now, we have to look up our states, and the reason really, besides just knowing if it goes through or not, we need to know what the precipitate is, which is going to be the solid. So you look up your states. K2S, I happen to know that all potassiums are always aqueous, and lead-2 phosphate, that's definitely going to be the solid one. So the term precipitate is the solid that forms. That's going to be this one. So this is where my X is going to be. But we have to balance it first. So let's see. I'm seeing 3 leads here. Let me put a 3 there. That gives me 3 sulfurs. Let me put a 3 there. That gives me 6 potassiums. So let me put a 2 there. And that gives me 2 phosphates, 2 phosphates. So my mole ratio is 2 to 3 to 3 to 1. Let me double check to make sure that seems right. Let's see. Yeah. So I'll put the 1 here. Okay. So the problem says this many grams of potassium phosphate, which is this. Okay. So the first thing I have to do is convert that into moles. So 4.37 grams of potassium phosphate. So let me look this up. So potassium is 39.098 times 3. So that's my 3 potassiums. Let me do the 1 phosphorus, which is 30.97. And let me add my 4 O's. That's easy, 64. All right, so the molar mass of this is 212.264. And again, that's the number of grams that equals 1 mole. So since I want to convert grams to moles, I'm going to put my 1 mole on top, and I'm going to put my 212.264 grams on the bottom. Cancel, cancel, and let's see what we get. 0.0206. And that is how many moles of potassium phosphate. So I'm going to write that right in my table. Man, this board calibration is off again. 0.0206. All right. So the problem says what mass of the precipitate should form. I don't care about this. I don't care about this. I only care about my solid precipitate. So here's my X. So again, you can work this out by saying 2 over this equals 1 over x and cross multiply. But I'd say do this quicker by looking at the mole ratio. It's a 2 to 1 mole ratio. So for every 2 that go in, you get 1 out. So you're going to take this number and divide it by 2, and that should give you your answer. And we can do that in our heads. So x is going to equal half of that, so 0.0103 moles. And again, that's moles, not grams, of lead to phosphate. Oh, that's going to be fun to do a molar mass. Well, let's do it. Because basically what we have to do now is convert these moles into grams. So, 3 leads, 207.2 times 3. 2 phosphoruses, so plus 2 times 30.97. Plus 8 O's. Well, what did I say before? 64 was 4 O's, so 128. So my total molar mass is 811.54 grams. So let me do that right here. So I have 0.0103 moles times 811.54 grams per mole. Mole cancels mole. Let's see what we get. 8.36. 8.36, and the unit is grams. Okay? By the way, just a quick note here. This might almost seem like a violation of the law of conservation of mass, because if you're putting 4.37 grams in, how are you getting 8.36 grams out? That's almost twice as much. Well, don't forget, there's another reactant here, and there's another product here that's kind of accounting for that other mass. Technically, if you did add up everything involved, it would have to be perfectly even. All right, so that was a mass grams in, grams out problem. That leads us to percent yield, which is a very simple concept. So the way I like to explain this is kind of with a story. Imagine you're like a corn farmer, and you do all your research over the winter, and you buy all the fertilizer, and you buy all the seeds, and you make all your calculations, and you plant you plant the crops, and then you sit down with your clipboard and your calculator, and you say, okay, based on everything I've done, in theory, I should get 100 units of corn. I don't know what you want to call them. Let's say I want to get 100 units of corn, in theory. But obviously, theoretical is never really true. So let's say, some crows come and eat some of the corn. Let's say there's maybe a drought or a flood. Maybe it's a little too cold. Maybe it's a little too hot. And let's say what he actually gets is 85 units of corn, actually. So how much a farmer gets is called the yield. I mean, that's like a legit farm term. So it's kind of similar here, where this farmer was expecting 100, in theory. He only got 85. So what's his percent yield? 85%. Well, just like in chemistry, when you're trying to collect a sample of something based on a reaction, you do the math. You sit there with your periodic table and your calculator, and you work out how much you should get. In theory, I should get this much of my product. Well, how much you actually get depends on a lot of things as well. Maybe the temperature was off. Maybe some spilled. Maybe some fell out of the side of the beaker. How much you actually get is not going to be equal to how much you should have gotten. Now, in chemistry, this often works in both ways. It'd be kind of, strange for the farmer to get more than he planted. But in chemistry, a lot of times you can get more than you expected. And really what that means is you probably just made an error and underestimated how much you actually put in. Maybe if you measure 5% less of your reactants, you might get 5% more of your products. So it's not like you're creating matter or anything like that, but it just means that you maybe messed up a calculation. So anyway, let's go through the percent yield formula. It's very simple. Percent yield. It is the experimental yield divided by the theoretical yield. Experimental yield divided by the theoretical yield. Now, experimental means what you got when you did the experiment. Sometimes we call this the actual yield, meaning like what you actually got, but I prefer calling it the experimental yield. Because when I think actual, I think like what it should actually be, but no. Experimental is what you get during the experiment. Theoretical means what, in theory, should you have gotten, and that's what you work out when you do the math and when you do the stoichiometry. Now, some textbooks tell you to leave this as is, so you can end up getting a positive or, actually, no, you can never get a negative. Yeah, but, yeah, so we don't need, I was about to say, but the absolute value lines, but no, that's only percent error. What we are going to do is say times 100%. So that turns it into a percentage. Okay. Now, percent yield usually exists just as kind of a tack-on problem onto the end of like a mass problem. So, for example, we just worked out this problem. Right? Well, what I did was I tacked a little percent yield onto the end of it. So let's go back and see what I actually got once again. So I said you mix this many grams of potassium phosphate. What mass of precipitate should form? Now, how much should form? What is that going to be? Experimental or theoretical? Well, that's going to be theoretical. In theory, on paper, how much should you get? 8.36 grams. So 8.36 grams equals the theoretical yield. Okay? Well, according to the problem that I said here, if 6.29 grams of precipitate form, meaning if that's what you get during the experiment, well, that's going to be your experimental yield. So let me write that above it, just for ease. 6.29 grams equals the experimental yield. So the formula, experimental yield divided by theoretical yield, I can tell that's probably going to be about 80, 85%. Let's see what we get. So 6.29 divided by 8.36 grams divided by grams, units cancel. 6.29 divided by 8.36. 0.752, 0.752, but we're going to say times 100%, so that's going to become 75.2%, and you have to keep your same sig figs. So 3 sig figs from my experimental, or actually, well, yeah, that led to this. 3 sig figs here, 3 sig figs here, so 75.2% is my percent yield. All right, let's do one more. This is kind of a from-scratch problem with percent yield. So it says 83.5 grams of water is fully decomposed in an electrolysis lab setup. So let's write out the formula. H2O. Electrolysis means it's going to decompose into hydrogen and oxygen. Both of those are diatomics, Brinkelhoffs. Let's balance it. So we need a 2 there and a 2 there. So my mole ratio is 2 to 1. So I tell you how many grams of water fully decomposed. I tell you the oxygen gas is captured. And here I tell you if 45.3 grams of oxygen gas is captured, actually during the experiment, what's the percent yield? So what we need to do is figure out how much you should have gotten. That's your theoretical yield. We're then going to get that and compare it to the 45.3 grams. So we're going to set that off to the side for now. Let's work out the theoretical yield first. So 85.3 grams of water. I can't just say 85.3 here because that's not moles, that's grams. You have to convert to moles. So 83.5 grams of H2O. Now water is one of these that if you've done it enough, you just got it memorized. It's 18.02. So times 1 mole over 18.02 grams, that's 2 H's and 1 O. 83.5 divided by 18.02. And I got 4.63 moles. So that's my water. So I'm going to say 4.63 moles of water. All right, well, I'm looking for how much oxygen. Gives no mention of hydrogen. I don't care about hydrogen. I'm going to leave that alone. Now, you can work this out in 2 ways. So here's my x. You can work it out by saying 2 over this equals 1 over x. But I'd say it's easier to just look at the mole ratio. It's a 2 to 1 mole ratio. So you're going to get half as much. So let's divide that by 2 to get half as much. So 4.63 divided by 2 gives me 2.315. I'll call it 2.32 for sig figs. That's how many moles of O2 are going to form. In theory, in the perfect world, this is exactly how many moles you'd get. Well, this is my theoretical yield, but it's in moles. We need to get this into grams. So fortunately, O2 is pretty simple. It's 32 grams per mole. So I'm going to say 2.32 times 32 gives me 74.2 grams of O2. That's how much should form, in theory. So that's my theoretical yield. Well, now we go back to the problem. It says if 45.3 grams of oxygen gas is captured, what's the percent yield? So let me write this over here. 45.3 grams, that's my experimental yield, divided by my theoretical yield, 74.2. Looks like it's going to be about 60% or so. So 45.3 divided by the answer gives me 61.0. 61.0%. And that's how you report your answer. Okay. So I worked out set up 4 problems here. I suggest you pause, try to work through these, and then unpause and go through the video. All right. Number 1, I have 2.3 moles of aluminum chloride placed in a tank containing excess fluorine gas. This term excess, it basically means you have enough of the fluorine gas that it's not going to run out. This is something we're going to learn later in Unit 8. There's a limiting and an excess reactant. Basically, if I give you both amounts, like if I say 2.3 moles of aluminum and 4.6 moles of fluorine, one of them is going to run out first. So they can't both be used up. But if I just say excess, it means there's enough of it that it's not going to run out. So it really doesn't affect our math in this type of problem. Let's write out our formula. Aluminum chloride, AlCl3, are placed in a tank containing excess fluorine gas, so F2 gas. How many moles of chlorine gas are produced? Well, let's see if this will go through first, so you can check your activity series. Fluorine is going to try to bump chlorine out, single replacement reaction. Yes, it can do so. Fluorine is the most active halogen. So the fluorine is going to bump the chlorine out, so we get AlF3. The chlorine gets bumped, and since it's a Brinkelhoff, it is Cl2, and I told you it's a gas here, so we can write that in. And now we go back and balance it, so I'm seeing 2's and 3's. When I see 2's and 3's, I think 6. So I want to get my fluorines to 6 by putting a 3 there and a 2 there. That brings my 2 aluminums, 6 chlorines, 6 chlorines. So my mole ratio is 2 to 3 to 2 to 3. All right. Given the problem moles, so this is a moles in, moles out problem. This should be pretty straightforward. If 2.3 moles of aluminum chloride, 2.3, how many moles of chlorine gas? X. So you can set this one up with your cross multiplying, or you can just work it out. So let me show just working it out based on mole ratios first. So I'm seeing a 2 to 3 mole ratio. 2 to 3. When I see 2 to 3, I'm thinking, how do I get from 2 to 3? Well, you multiply by 1.5, by 1.5. So I'm going to multiply the 2.3 times 1.5, because that's the same thing here. 2 to 3 ratio, multiply this times 1.5, and that's going to get us our answer. 2.3 times 1.5, and with my 2 sig figs, I'm going to say 3.5. X equals 3.5 moles of Cl2 gas. Final answer. Let's check the other way and just make sure it works. Okay, ignoring the red lines going through my equation there. All right, so the way you set it up the other way is you would say 2 over 2.3 equals 3 over x. Let me rewrite that. 2 over 2.3 equals 3 over x. And now you cross multiply to solve for x. So 2x is going to equal 3 times 2.3. Okay, board calibration is way off again. 3 times 2.3 is 6.9. divided by 2 gives me 3.45, which is my same 3.5. You get the same answer. All right, number 2. A piece of copper wire, a piece of copper metal is burned in a Bunsen burner, forming copper 3 oxide. So let's write our formula first. Copper metal, Cu solid, burns in a Bunsen burner. That just means it burns in air, forming copper 3 oxide. Isn't that the same example I gave? Well, similar problem, but we'll still work it out. So it's going to form copper 3 oxide, so it's going to be Cu2O3. Let's balance it out. I need a 3 there, I need a 2 there, and I need a 4 here. So it's going to be a 4 to 3 to 2 mole ratio. So the question says, if I put 14.2 grams of, oh, I see, I'm telling you how much of the product formed. I'm telling you 14.2 grams of this formed, what mass of oxygen gas must have been consumed? So it's still a grams in, grams out problem. It's just kind of working backwards. So I need to find out how many moles of this went in, not grams. I cannot just say 14.2 and then get that ratio because it's not a grams ratio, it's a moles ratio. So let's work it out. 14.2 grams of Cu2O3. I need to look up my molar mass. So I should have just saved it from before. 2 coppers, that's 63.55 times 2, plus 3 oxygens is 48. So 175.1, but I'm going to say times 1 mole over 175.10 grams. Gram cancels gram. Let's see what we get. 14.2 divided by that answer gives me, and I'm going to go ahead and I'll write it here first, 0.0811. Looking at my sig figs here. And that's moles of copper 3 oxide. So I'm going to write that in right here. 0.0811. Well, the problem says what mass of oxygen gas was consumed. So here's my x. Again, you can say 2 over this equals 3 over x and cross multiply, but I prefer to look just at my mole ratios. It's a 2 to 3 mole ratio. So to go from 2 to 3, you multiply by 1.5. So let me multiply this by 1.5, and that'll give me my answer. So times 1.5 gives me 1.2, not that, 0.122. 0.122, and that's moles of O2. Okay, but I'm not looking for moles, I'm looking for grams. Fortunately, oxygen gas is real easy, 32. So times 32.00 grams per mole gives me 3.89. 3.89 grams of O2 gas. And that's my answer. Okay. By the way, looking at this in terms of conservation of mass, notice you're developing 14.2 grams of the product, but only 3.89 grams of oxygen went in. I'll bet if you ask the question how much copper formed, I'll bet it would be the difference there. I mean, in theory, it has to be exactly the difference because there's conservation of mass. I'll bet, that's about 4, this is 14. I'll bet this work out to a little more than 10 grams. All right, number 3. In the whoosh bottle demonstration, that was that big jug of Poland Spring water that whooshes out. 20.0 grams of ethanol, C2H5OH, combust. So let's write out our equation. C2H5OH. Now here's the thing. The OH on the end is important in terms of like the real chemistry to show that it's an OH group at the end. This is kind of advanced levels of organic chemistry. But for the sake of balancing, I'm going to put my O's and H's together. I'm going to call this C2H6O. And that's perfectly acceptable when it comes to balancing. In fact, if you Wikipedia ethanol, it'll usually list it as this and that. So that's my C2H6O. That was liquid. Actually, it was aqueous technically. I'm going to leave the state out of this because it's not entirely clear. Yeah, the ethanol I used was a mixture of ethanol and water. But we'll leave it as this ethanol. Plus O2 gas yields CO2 plus H2O. All right, let's balance. Let me rewrite that 6 so I can see it more clearly. All right. Start with hydrogens. So 6, I'm going to put a 3 here. Now normally 3s are not a good idea because it'll make my oxygens odd, which I can't have. So I say when in doubt, double it. But here's the thing. This extra O here makes it odd, so this might work out. Let's see. Let me leave that there. For carbons, let me put a 2 there for my carbons. So my oxygen should be able to work out now. So I have 2 times 2 is 4, plus another 3 is 7. I need 7 oxygens on this side to balance out. Now I could put numbers in front of this to get more O's here, but that would throw everything else off. That would throw my C's and H's off. So let me leave the 1 here, meaning I need 6 more, and I'll put a 3 there. So 1, 3, 2, 3 is my mole ratio. All right, the problem says 20.0 grams of ethanol combust. If 1.15 grams of liquid water are recovered, what is the percent yield? So this is going to be a percent yield problem, so I need to work out the grams in, grams out. So my goal is this. I need to figure out if I put 20 grams of ethanol in, how much liquid water should I get? That's theoretical yield. Let's work it out. So first I need to convert my 20 grams of ethanol into moles. So let's do the math here. So carbon is 12.01 times 2. I have 6 hydrogens, so that's plus 1.00794 times 6. And I have 1 oxygen plus 16. So my molar mass is 46.07 grams per mole. Let me work this out. 20.0 grams of ethanol times 1 mole over 46.07 grams. And let's see what we get. 0.434 moles. So that's how many moles of ethanol I used. 0.434. All right, we're looking to figure out how much water I should have gotten. So here's my X. And I hope by this point you can kind of see where I'm going with this. I see a 1 to 3 mole ratio. So instead of cross-multiplying and wasting time, I'm just going to say, look, if it's a 1 to 3 ratio, I'm just going to triple this number, and that would give me X. So this times 3 gives me 1.30 moles. That's how many moles of water I should get. So I need to convert the moles of water into grams of water to see my theoretical yield of water in mass. So 1.30 moles times the molar mass of water, which again I've had memorized, 18.02 grams per mole. And we get 23.43. Let me look at my my sig figs, 3 sig figs. So 23.4 grams of H2O. Now, this is making me a little concerned because normally when I write these types of problems, I like to make the experimental yield kind of close, which means I either made a mistake here or I made a mistake when I wrote the problem. Let me do a quick look over to see if this makes sense. So 2 carbons is 12. Oh no, that's 24. Okay, this seems about right. Okay, so it's a 1 to 3 ratio, right? I didn't mess that up. Yeah. So, yeah, times 18. I trust my numbers here. So hopefully I made a mistake before and not now. But hopefully you'll call me out on that if you see it. So this is my grams of water that I should get. My theoretical yields is 23.4 grams. Well, what did I actually get? I actually got just 1.15. So this is going to be a very small percent yield. So 1.15, that's my experimental yield. That's what I actually got. Divided by 23.4 grams. 23.4, 1.15 divided by 23.4 times 100, 4.91%. 4.91%. And that is my final answer. All right, number 4. So, solutions of, so this is aqueous here. Solutions of potassium phosphate, that's going to be K3PO4, aqueous. And magnesium acetate, MgC2H3O22, aqueous. Let's finish out our equation. Potassium is going to bond with acetate, forming KC2H3O2. I know that one's going to be aqueous because I know potassium is always aqueous and acetate's always aqueous. Magnesium is going to bond with phosphate. So 2 plus 3 minus gives me Mg3PO4 2. And I know that one's going to be solid. You look it up on your chart, it's going to be solid. So this reaction will take place. Let's work out the coefficients, the balancing. So I'm seeing, let's see, I'll start here. I see 3 magnesiums. So let me put 3 for magnesiums. That gives me 3 times 2 is 6 acetates. Let me put a 6 there for 6 acetates. 6 potassiums, 6 potassiums. 2 phosphates, 2 phosphates. So my mole ratio, 2 to 3 to 6 to 1. All right, let's see what we're asking. If 0.31 moles of potassium, very generous, I offered it in moles, saved you a molar mass calculation. So potassium phosphate is this one, so 0.31 moles of potassium phosphate fully react. How many moles of each reactant, ooh, typo, what should I have said? Product, obviously. How many moles of each product will form? Well, let's work it out. I'll call this X and Y. So, hopefully by now you see kind of where I'm going with this. Instead of working out by cross-multiplying, I like to look at the mole ratio. It's a 2 to 6 mole ratio. 2 to 6, that's like 1 to 3. So basically, you're going to triple the number of moles. For every 2, it's going to form 6. So for this, I'm going to multiply it by 3. And that X is going to equal 3 times that, which is 0.93 moles. That's moles of potassium acetate. Okay, so here, we actually have a couple options. You can use this and get that. You can say it's a 6 to 1 ratio. Let me divide that by 6. But I think it's easier to look at the 2. So it's a 2 to 1 ratio. So you're going to get half as much, so let's divide that by 2. 0.31 divided by 2. So y is going to equal, with 2 sig figs, 0.16. 0.16 moles. And just to check, if you had done it this way, if you got this answer and then used it to get this answer, you're probably going to have this exact same thing. It might be a little off due to rounding. Let's see. So if you had 0.93 and it's a 6 to 1 ratio, you're going to divide that by 6, which gives you the exact same answer. So you can do it that way as well. So the first part is done. I formed how many moles of each product? Well, it's going to be 0.93 moles of this product and 0.16 moles of this product. Now let's work out, it looks like I gave a percent yield as well. So if 35 grams of precipitate are collected, what is the percent yield? So first you have to know what the precipitate is. It's going to be the solid product, magnesium phosphate. Okay, so I figured out how many moles I should have produced in theory. This is how much you actually got during the experiment. So what I need to do is convert my moles into grams to find out how much I should have gotten in grams. Let's do that. So magnesium phosphate, I'm going to have 3 magnesiums. So that's 24.305 times 3. I have 2 phosphoruses, so plus 2 times 30.97. And I have 8 oxygen, so plus 8 times 16. So my total molar mass for magnesium phosphate is 262.855 grams equals 1 mole. So let's work it out. 0.16 moles. Again, that's the theoretical yield. That's how many moles I should get in theory. Times 262.855 grams per 1 mole. Cancel, cancel. Let's see what we get. Hopefully this one works out better than the last one. It looks better. So, in theory, I should get, according to my math, with 2 sig figs, 42 grams. 42 grams of precipitate. How much did I actually get? 35. So it looks like I got about 80%. So, we do the math. We say 35 grams divided by 42 grams. 35 divided by 42 times 100% is going to be 83.333 repeating. But of course, we're not going to say that repeating, and we're never going to do that line above the 3. This isn't math class. You would say 83% with 2 sig figs. 83%. Okay, so that is it.